In the following video, we are going to observe the design and analysis of finite elements of porous materials applied in the space field. The Crew Exploration Vehicle called Orion, developed by NASA, allows astronauts to be taken beyond low Earth orbit. This vehicle, during its descent, is subjected to multiple forces and effects. But what we are going to focus on is the G-force suffered by the astronauts inside the vehicle. More specific in the impact on the seat section. The human body during these missions tends to support loads of 10 G, where it decomposes in different directions depending on the rotation of the vehicle. To analyze the impact of the G-force at different points, the rotation matrix is used. For example, suppose that during an emergency landing, the Orion vehicle undergoes a 45 rotation around the y-axis at the moment of impact. We want to calculate how the forces measured in the seat coordinate system transform into the vehicle coordinate system due to this rotation. First, let's define the two coordinate systems. These coordinate systems allow us to understand how forces acting on the seat translate to the overall vehicle. Now, let's assume the vehicle rotates 45 degrees around the y-axis during the landing. To transform the forces, we need a rotation matrix. For a rotation around the y-axis, the rotation matrix is defined as substituting 45 degrees for theta. We get this matrix will help us rotate our forces from the seat's perspective to the vehicle's perspective. Let's imagine that during the impact, a force of 800 newtons is measured acting upward in the seat's z direction. This force could result from the vehicle decelerating when it hits the ground. The force vector in the seat's coordinate system is. Now, we need to transform this force into the vehicle's coordinate system. To transform this force, we multiply the force vector by our rotation matrix. This gives us the transformed force in the vehicle's coordinate system. Performing the matrix multiplication, we get, so the force that was originally 800 and upward in the seat system is now split into two components in the vehicle system, 565.69 and upward, and 565.69 and forward. With this, we can define how the forces act on the seat of the vehicle, and also on the person. This study focuses on the use of porous material to withstand the forces to which the seat of the Orion vehicle is subjected, guaranteeing the safety of the astronaut. We worked with two different types of TPM's lattice, and varying the porosity with 60 and 30. Then through finite element analysis the deformation suffered by the material was determined. This is because, according to studies of human systems integration requirements, to avoid injuries in the axis of the upper area of the body, there cannot be a displacement greater than 50 mm and 25 mm to guarantee the physical state of the astronaut. The porous materials were simulated with nylon 6 and TFE. Once having all the samples, a Taguchi design was made where in order to maximize the deformation, since they are semi-red materials, the best configuration was found, finding that the percentage of porosity and the material are the key factors to take into consideration.